Our third and last video for this unit talks about our last two types of reactions. So we're going to start with a talk about single displacement reactions, and then we're going to look at double displacement reactions. So definition of a single displacement reaction, it's where you have an uncombined element replacing an element that is part of a compound. And there are two types that we're going to look at. So I always have a metal or an element by itself in a compound. So element plus compound. If you have that, you could have a single displacement reaction. And what will happen, element, I can't spell. What will happen at the end is that you will have a new element that's by itself and not bonded to anything else, and a new compound. So that's what you're sort of looking for in the general equation of a single displacement reaction. So here are two examples that you see a lot in the lab. So here is a metal replacing another metal. We have copper metal that's all by itself, and silver metal that's in silver nitrate. So what will actually end up happening is if we do this reaction, the copper replaces the silver, so bumps out the silver. So now copper is bonded to your nitrate, and your silver is left all on its own. And then the other one here is what we did in one of our first labs when we looked at the trends in the periodic table. We were looking at the alkali metals reacting in water. What happened in that case was that the sodium metal, when it went into water, it actually bumped out a hydrogen. So the hydrogen actually sort of acted like a metal in that lab. So we had the sodium bonding with your OH ion to make sodium hydroxide. And then the hydrogen made hydrogen gas, H2. So both of those are examples of a metal that's by itself bumping out something else from a compound. The activity series, this is a really important concept, and this was in your lab that we did the other day. So this is used to predict if a single displacement reaction involving metal will actually occur. Sometimes what happens is you will mix these two things together and you will see no reaction. So the rule is that each metal will displace any metal ion that appears below it in the series, and this is in your textbook as well as on the slide here. You will always be given an activity series. You do not have to memorize it. So here, if I use this activity series of metal that's on my slide here, each metal will displace any metal ion that appears below it. So let's look at my first example. I've got aluminum. If it's going to bump anything out of here, it's going to bump out iron. Okay, so if my aluminum comes and bumps out iron, then iron would be all by itself. Now this will only happen if iron is below aluminum on the activity series. So let's check the activity series over here. So where is aluminum? So here's aluminum here, and here is iron here. So iron is in fact below aluminum. So this will actually happen. So basically what it's saying is that aluminum almost has enough energy to bump out the iron, and then aluminum bonds with oxygen instead, and iron is left all by itself. If it happens that the element is not below the element that's by itself, then no reaction will occur. So let's check this one out. So if I've got zinc, it's going to try and bump out magnesium. If it doesn't have enough energy, this actually won't happen. So let's take a look here. Where is my zinc? Here's zinc. Okay, right there. And magnesium is actually above it. So magnesium has more reactivity than zinc, which means that zinc does not have the energy or does not have the reactivity to bump out magnesium. So no reaction will occur. That's what the symbol NR means. It means no reaction. So it doesn't matter how much magnesium nitrate I mix with how much zinc, nothing's going to happen to either of these compounds. All right, the second type of single displacement reaction is where you have a nonmetal replacing another nonmetal, okay? So we looked before at metals that bumped each other out. Here we're looking at nonmetals replacing each other in a compound. So the activity series for halogens is the most common one that you need to know, and it's straight off your periodic table. So if you look at the order that's here on my activity series chart, it's the same order that your halogens appear on your periodic table. So you actually don't need an activity series because you can just look it up straight on the periodic table. So same rule applies. An element will bump out anything as long as it's below it on the periodic table. So example, chlorine is going to try and bump out another nonmetal. In this case, it's going to try and bump out bromine. So is bromine below chlorine? Yes, in fact it is. So this reaction will happen. Bromine will end up all by itself, and my chlorine will bond with my hydrogen. In the second example, iodine is trying to bump out chlorine. But if you look here, iodine is below chlorine. It's not above it, so it doesn't have enough reactivity to make this happen. So we write no reaction, or NR. All right, so that's it for single displacement reactions. The next and the last type of reaction that we're looking at is a double displacement reaction. So double displacement reactions is where you have different atoms in two different compounds, and they replace each other. And these two compounds basically react to form two new compounds. So here is our general formula, where you have compound AB and compound CD. And basically what happens is A and C switch places. So you get A bonding to D and C bonding to B. Okay, so that's the general formula. Let's go through some examples. So magnesium carbonate, which is an antacid, reacts with hydrochloric acid in your stomach to form magnesium chloride and carbonic acid. So what actually ended up happening here? Your magnesium and your hydrogen actually switched places. Okay, so the hydrogen ended up bonding with the carbonate. That's your carbonic acid. And the magnesium ended up bonding with the chlorine. That's your magnesium chloride. Okay. The trick that I always tell my students to do is you're going to be playing with ionic compounds a lot in these types of reactions. So when you predict your products, you're going to have to do C, 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 C. Check your charges and crisscross to make sure you get the right formula. So seeing as though you have to check your charges anyways in order to do this, throw your charges over on the reactant side. So if I do that, my magnesium has my positive charge, carbonate's going to have the negative charge, hydrogen's going to have the positive charge, and chlorine's going to have the negative charge. Then what you do, you take your two positive charges and you swap them. And if you do it that way, you'll never make a mistake. In your stomach, if you want to finish this reaction, the carbonic acid, so the H2CO3, will actually decompose into carbon dioxide and water. Okay, and that was back on our first video of this unit. This is the decomposition of an acid. Okay, so if you need to review that, go back and watch the second video. Let's get rid of that writing. There we go. So, types of double displacement reactions. There are three types you need to know about. The first is ones that produce a precipitation, and these are sort of the most common ones that we do in the labs in grade 11. So it's a double displacement reaction that produces a solid. And that solid is what's known as a precipitate. So the precipitate can be removed by filtration, which is what we're actually going to do in the lab. And you're always given a solubility chart. It's in your textbook. It's also here on your slide, and it's always going to be given to you for a quiz or for a test, so you don't have to memorize it. But what we do is we use it to predict if a precipitate will be produced in a reaction. This is a little bit challenging for me to do in a video, so I want you to just kind of take my word for it for now, and I will show you how to use the solubility chart when you come to class. So basically what it does is, here is again a double displacement reaction. I have two compounds making two new compounds. If I put my charges above each one, so I know the metals are always positive and my nonmetals or my polyatomics are always negative, my two positives are going to switch. So my calcium is going to bond with my carbonate, and the sodium ion is going to bond with chlorine. So I make calcium carbonate because these two switch. So calcium carbonate's one of my products, and sodium chloride's one of my products. That will only get you part marks in this course. The second thing you have to do is be able to predict the states. So if you look here, I've actually written a solid beside calcium carbonate. Okay, that means that if I mix these two compounds together, I will make a white goopy solid in the bottom of my beaker, and that is identified as calcium carbonate. My sodium chloride will remain dissolved in water, and I can write aqueous there. So what I'm going to do in class is I'm going to teach you how to use a solubility chart so that you can predict which one is the solid all on your own. Our last two types of double displacement reactions are reactions that produce a gas and neutralization reactions. So here's a reaction that produces a gas. Again, it's a little bit tricky to see, but you can still do your positive and negative charges and then swap the two positives. And that gives you H2S. So my H bonds with my S, bring me H2S, and then my Na, which is positive, is going to bond with the Cl, which is negative, and make sodium chloride. Now this isn't a double displacement reaction that makes a precipitate, because if you look at your products that I've written here, none of these are solid. So sodium chloride is still dissolved in water, it's aqueous, and I've made hydrogen sulfide gas. So I'm not actually going to make a precipitate in this reaction, but it still is a double displacement reaction, so it's still classified under this. The last one, and this should say number 3, is a neutralization reaction, which is a reaction between an acid and a base, produces an ionic compound, which is commonly referred to as a salt, and usually water. So for example, the example that's happening in this picture is this here. So the magnesium hydroxide is reacting with carbon dioxide and making magnesium carbonate and water. So here's what actually ends up happening is this carbonate turns into, or sorry, the carbon dioxide turns into a carbonate and makes that reaction happen, okay? A more simple reaction I will show you. So that's sort of a more complicated one that I wanted to show you, but I'm going to show you an easier one. So here's another example. Okay. So an easier one would be something like, here's an acid, sulfuric acid, and let's do lithium hydroxide. So when we, again, if we add in all of our positive and negative charges, and then we make the positive charges switch places, I end up with lithium bonding to sulfate, so LiSO4. Check your charges in crisscross, I get Li2SO4. And then I have H and OH coming together, which is the same as H2O. So the general equation is that we have acid plus base gives you a salt, or an ionic compound, plus water. So that's your general formula for neutralization. Again, this salt here is usually aqueous, so I'm not making a precipitate. My water is a liquid, so again, I'm not making a precipitate. I'm not making a gas, so this type of reaction doesn't fall under any of the other double displacement reactions, so it's in a class all on its own. So we're going to do a bunch more of these in a lab, and a bunch more examples as a class so that I can show you how all of these reactions work.